structure and hybridization of alkenes. The example shows a typical alkene that is characterized by a carbon-carbon double bond. Alkenes are unsaturated compounds because the maximum number of hydrogen atoms are not bonded to the alkene double bond system. Two hydrogens must be removed to make the double bond, and this makes the general formula of an alkene CnH2n and not CnH2n plus 2 like in the case of the alkanes. The structure of an alkene is characterized by this flat part where all these atoms are in the same plane. This is created by linking two sp2 carbon atoms. The bond angle between the groups around an sp2 carbon atom is 120 degrees. Let's go and look at the structure a little bit in more detail. This is the most simple alkene, ethene, and if we optimize the structure and we measure the bond angles, we see that the bond angle between the hydrogen, the carbon, and the other hydrogen is almost, if we round it off, it will be 120 degrees. If we look at the bond angle between this hydrogen, the carbon, and the other carbon, it means that angle there, it is 120 degrees. So all the groups around an sp2 carbon atom has got a bond angle of 120 degrees. Let's go and look at a more complex example. Here we've got an alkene with single bonds and double bonds, and the idea is to compare these two. So here is the alkene where all this hydrogen and the carbon is in the same plane. And let's measure the distance now between the atoms, the bond length. The bond length between two carbons with a single bond is 151 nanometers. If we compare that with the bond length of a double bond between these two carbon atoms, we find that it is 134 nanometers. It means that the double bond is much shorter than the single bond, and that will always be the case. We will also see that a triple bond is always shorter than a double bond. So how is this structure created? How do we create the sp2 hybridization? Carbon has got valence electrons in the second level. So we've got a 2s orbital. We've got 3 p orbitals available to place the valence electrons. So if we want sp2 hybridization, we mix an s and 2 p orbitals. 3 orbitals are used to create 3 new hybrid orbitals. So 3 sp2 orbitals. These sp2 orbitals are situated around each of the sp2 carbon atoms. The p orbital here is not hybridized. So a carbon atom with an sp2 hybridization has 3 sp2 hybrid orbitals, which looks approximately like this. To make the bonding in the alkene, we need to overlap another sp2 orbital from another carbon atom, and in this way we create the structure of the alkene. The head-to-head overlap is a strong sigma bond. The p orbital that is not hybridized is perpendicular to the carbon atom. On each carbon there is a p orbital, and sideways overlap of these, both below and above the level of the carbon atoms, create one pi bond. So this line and that line together is one pi bond. So that is the weaker pi bond because it's sideways overlap, which is not as good as head-to-head overlap. To bond the hydrogen atoms to the carbons, we must use the 1s orbital of the hydrogen atom, and this overlap there is the sigma bond. The sigma bond between the carbon and the hydrogen. It's an overlap of an 1s orbital with an sp2 hybridized orbital of carbon. We can now see why Alkenes react with electrophiles. This is an electron-rich system, and the electrophile would like to bond to this electron-rich system. So the pi electrons can easily be used to bond to this electrophile.